So Rachel, as we were saying before, you have the original right angle triangle ACB, and then you draw an altitude to the hypotenuse to make a right angle on the hypotenuse, and then you have two smaller triangles, and you still have the original triangle. What the theorem says is that each of the smaller triangles is similar to the big triangle, and then in addition to that, so you have two similarities already. Each of the smaller triangles is similar to the big triangle, so you have two relationships already, and then the third relationship is that each of the smaller triangles are also similar to one another. Now, what you must do always is be careful to arrange, to label properly the triangles in the right sequence. Label their vertices in the right sequence. This will help you in order to be able to use this information to do what this chapter is really leading to. Here's what I mean. So, for the original triangle, let's say we want to draw it so that we keep the right angle here. So that's this point, so that will be point C. What I call the shorter leg of the big triangle, the original triangle, the shorter leg goes from C to B. So this being the shorter leg, I'll call this my B. And therefore, automatically, this will be A, because it's A is the only thing left after we named C and B. So that's so now we have reoriented it because we want all of them to be oriented this way. So let's take the second one. Let's take this one. Okay. So that's the bigger of the two new triangles, the bigger of the two new triangles. And what would that look like if we orient it the same way? Well, we're going to have, well, it's already properly oriented actually. You see, that one is already well oriented, so we just copy it down here because its right angle is already here. So it's like that. And we don't need to do too much. That's D right here, the right angle, C, and A. So that one was already oriented the way we want it. Let's go to the last one. B, this last one, the smallest of the three, or the smaller of the two new triangles, okay? So again, we want the right angle to be here, just like these other ones. And how you then do the short leg in this case, look at that triangle shaded red. So the short leg is from D to B, where the right angle is. So again, we put D right here, because that's where the right angle is. And then B is the short leg. And then the only other point left is C. So now, it's very easy for us to see the relationships. So the first one is that this is similar to this. This is also similar to this. That's the second. And then the third relationship is that this is similar to this. So let's write all of them. So triangle ABC is similar to triangle ACD. We must go in the right order. So we went A, B, C, so we must go in the same order. A, C, D. That's not relationship number one. Relationship number two is that this is also similar to this. So that is, again, triangle A, B, C is similar to triangle. So we go C, B, D. And then the final relationship, the third one, is that these two are similar. So that's triangle ACD is similar to triangle CBD. That's what the theorem says. Okay, Richard? Now, why is that theorem valid? Can we prove it? Well, let me quickly do that. I'm going to quickly do that, but that will mean I will erase my shading in here to be a little clearer. I will erase the shades of green and red. Okay, to prove that, you take this angle, let's call it X. If this angle is X and this is 90, what is this angle? I think you will agree with me that this is 90 minus X, okay? Because this a triangle ACD, all the angles must be 180. This one is 90, this is X, so that's 90 minus X. Now, we know that the entire angle here is a 90, right? So if this is 90 minus X, it means that this little bit here must be X. Then when we now take the smallest triangle, that's 90, that's X, therefore this must be 90 minus X. Well, what has happened? We have shown that we have, so let's take the first of the relationships, triangle ABC and triangle ACD. So that's ABC, the original triangle, and ACD, which is the bigger of the two smaller triangles. So look at them. Each one of them has a right angle. ACD has a right angle, and this one has a right angle. Then each one of them includes an angle X, right? X here for the, no, sorry, each one of them includes the angle 90 minus X. They do each, not X. The big one, the original big one, includes an angle 90 minus X, this one. And then the bigger of the smaller two, the bigger triangle, the smaller two, ACD, also includes an angle 90 minus X. So each one of those two triangles, each one of these two triangles, in this first relationship, each one has an angle that is 90 degrees, and each one has an angle that is X, 90 minus X. Well, it means that the third one, each one of them must also have the angle that is X. Because if two triangles have two angles that are the same, the third must automatically be the same, because all the angles must add up to 180 degrees. And we know, you know, that similarity of triangles just means that all the angles are the same. All the angles in the two triangles are the same. The sides not the same, but all the angles must be the same. It's a proportion thing, it's a ratio thing. So one triangle can be much bigger than the other one, but the angles must all be the same in both cases, and that's what makes them to be similar. So we've just proved that in this case, and that's why these two triangles are similar. The same, you can see the same when you do the big triangle, the initial triangle, and the smaller of the two. Use the same reasoning and you'll see that is the case. And then the two new ones, the two new triangles, the two smaller triangles, you can see that it's the same. Each one of them includes angle X. This one includes angle X. This one here includes angle X. And this small one, smallest one, includes an angle X. Each one of them includes a right angle. So therefore, the third angle, 90 minus X, is also the same in each one. So those two triangles are also similar. And so the third relationship is also true. So we have in fact proved the theorem at the beginning of section 7.3. I hope this is very clear. If it's not, let me know.